pleasure to have Professor Zaher Hani from University of Michigan. He used to be a colleague of us and a good friend of many of us, and he's going to talk about mathematical theory of wave turbulence. Please go ahead.
Okay, thank you, Shun and Andre, for the invitation. It's an honor for me to speak in this seminar. As Shun said, I have a Georgia Tech has a special place in my heart, and also the other organizing universities. I have spent at least 2 summers at UC Irvine as well, and I have very nice memories there. And also at San Diego, I have visited several times and have a lot of friends there. Okay, so going to math, we'll be talking about the mathematical theory of wave turbulence today. And what I will be discussing is everything is joint work with Yu Deng at the University of Southern California. So the subject of today's talk, or the overarching theme of today's talk, is Hilbert's, what is known as Hilbert's sixth problem. So what Hilbert's sixth problem asks is for an axiomatic derivation of the laws of physics from first principles. So what we mean by that, or the main example that Hilbert had in mind, is justify the laws of statistical physics starting from the laws of dynamics. So the laws of statistical physics or statistical mechanics, we know that they cover macroscopic quantities, things like temperature, pressure. And whereas the laws of dynamics, they govern microscopic quantities, things like particle trajectories and orbits, okay? And those laws of dynamics, they could be classical, they could be quantum. So the statistical laws, their key feature, or one of their key features, is that they are typically time irreversible. So what this means is that for example, the thing that we have in mind, or the easiest way to remember it, is think of the second law of thermodynamics. What this means is that there's a preferred direction of time, and in this direction of time, something happens. Like, for example, for entropy, entropy increases in the positive direction of time. Whereas this is not present in the laws of dynamics. So the way we say that is that the dynamical laws are reversible in time. And we all know that Newton's equation and Hamilton's equation are reversible in time. So in this justification that Hilbert is asking from us, in this justification of the statistical mechanics from first principles, there is a passage from something that is reversible in time to a law that is irreversible in time. Okay, and this is somewhat of an apparent paradox. Okay, this apparent paradox is called the creation of the arrow of time, which is happened because we pass from something reversible to something irreversible, and it comes as a result of some averaging and limiting operations. And anyway, Hilbert's sixth problem is exactly asking for a mathematically rigorous resolution of this apparent paradox. So we shall be interested in this problem in the context of nonlinear waves today. But before I go there, let me tell you the classical setting of Hilbert's sixth problem, or of one example of an answer of Hilbert's sixth problem, which is the Boltzmann's kinetic theory. So the setting of Boltzmann's kinetic theory is that you start with the system with n particles. Each of those particles has radius r, and we're thinking of those particles as undergoing elastic collisions. We assume that the initial state of the particles are random and independent. So we have many particles, but their state initially, their position and velocity is random and independent. So that each initial particle has, each particle has a density distribution, so the f naught of x v. So this means that the probability of finding this particle at position x and velocity v is given by this density function. And what Boltzmann's theory tries to find, or the aim of Boltzmann's theory, is to give the effective dynamics of the one particle density function at later time. So this is, if you think, you can think of it as the probability of finding a particle at position x moving at velocity at a later time. And the central object in this theory is Boltzmann's equation, which tells you that this one particle density function should be essentially satisfying this equation, which is Boltzmann's equation. And so there's a transport on the left-hand side, and on the right-hand side, there's a collision kernel, quadratic collision kernel, which I won't write here for the sake of brevity. And so Hilbert's sixth problem would correspond to a justification of this approximation between the probability of finding a particle at position x moving with velocity and the solution of Boltzmann's equation. And this was a big challenge. It was it was formulated as a rigorous mathematical theorem in Lanford in 1975, but this proof needed to be extended and completed, and this was done mainly in this work of Gallagher, San-Remo, and Texier recently. So what does Lanford's theorem tell us? It tells us that in the limit as the number of particles goes to infinity and the radius of those particles goes to 0, and so the key point, this is a central thing, is that this happens under what is called the Boltzmann-Grad scaling law. So n goes to infinity and r goes to 0, but not arbitrarily. They go to those limits such that n times r to the d minus 1 is always order of 1, stays bounded, okay? So this is what is called the Boltzmann-Grad scaling law. But in this scaling law, if n goes to infinity and r goes to 0 according to this scaling law, then we have the following 2 points. We have propagation of chaos. The states of the particles retain their initial independence in the limit. So initially, as I said, the particles were chosen, or the position velocity density was chosen to be random and independent. Of course, as the particles interact with each other, this very important property is exactly what we were after, is that indeed Boltzmann's equation is a faithful approximation for the one particle density function Fn1. Okay, and this approximation between the one particle density function and the solution of Boltzmann's equation holds in the limit as n goes to infinity and r goes to 0, and for times that are order of gamma inverse. So they are much smaller times than we would like. So this and even in later proofs, this was not something that was improved on, is still up to times that are order of gamma inverse. So they are fairly small times. And so this is an example of the kinetic framework, but this kinetic framework is highly informative and was generalized to much more general and other particle systems. Okay. So today we'll be interested in doing a sort of wave PDEs. So be and very shortly physicists, Peierls in 1929, and then Hasselman, and later on by Zakharov and his school. So in this setting, the microscopic dynamics are given by a nonlinear dispersive PDE, okay, rather than being of particles. We have a large number of waves here that are interacting with each other. And those waves are represented by the Fourier modes of the solution. And this solution is a set in a box of size L, and this is the L that will be going to infinity. So the size of the box will take the position that was taken by, or the role that was taken by the number of particles in Boltzmann's theory. And these waves undergo, we will think of those waves interacting, we think of them as collisions through the nonlinear interactions that are given by the dispersive system. So the dispersive system can be quite general, but for us today, we'll consider the nonlinear Schrodinger equation, which is given over here. So it's IDT plus Laplacian of V is equal to alpha V squared V. This alpha is inserted over here to basically to quantify the size of the nonlinearity. So alpha will stand for the size of the nonlinearity, and the PDE is posed on a box of size L with periodic boundary conditions. As such, I would denote this box by TD sub L, okay? So it's a torus of size L, with, if you like. Okay, and the dimension is greater or equal to 3. So why do we start by considering large importance as a system for nonlinear waves? And mainly this is in addition to the fact that it appears in so many different applications, but it satisfies a very important universality property, which tells you that virtually any Hamiltonian dispersive system will give you NLS in an appropriate scaling limit. Okay, so if you cannot do it for the NLS equation, you really have very little hope of doing the theory for any other equation. And okay, so this is a slide to justify why we need to think probabilistically or statistically about things. And the reason for that is the same reason that we think statistically in classical for the system of n particles that Boltzmann considered. So as in the particle case, the need for the statistical theory comes from the long time behavior of solutions. So so let me elaborate a little bit on that. So if you study those dispersive equation on a compact domain, like of what is of the solutions. We know that there are many different possibilities for this long time behavior. We have solutions that are periodic in time, quasi-periodic in time, soliton-like. So there's a zoo of different possible long time behaviors, and it's very hard to say whether, if you give me initial data, it's very hard to say whether, how does this initial data behave at later times. And this is, in a way, this is even true for finite energy solutions on RPE. This is a setting where we have a much better understanding of the asymptotic behavior of solutions. We know we can describe in that setting, in many cases at least, how the solutions behave as t goes to infinity. However, even though we can do that, we do not have a good understanding of the intermediate time behavior. We don't understand what happens to the solution in the intermediate times before it scatters. And this is, again, will be a setting where the kinetic theory will be very illuminating on such questions. So that's the reason why we start thinking probabilistically about the problem. And this moves us right away to the probabilistic setting of wave turbulence theory, which is also called, or also known as statistical mechanics for wave systems. Okay, so let me start by telling you a little bit about this theory. First, from the point of view of physics, or which I will state as a conjecture, and then we'll start discussing some rigorous results. So just like for many particles, or in the Boltzmann setting, we will start with the random distribution of initial data. So we'll take initial data for NLS now, that here, this is just the expansion of the initial data in terms of Fourier modes. But the key point is that I will take the Fourier modes to be random in a certain way. So we'll take the initial data, or in Fourier space, to be given by square root of n initial at k. And this n initial will be a non-negative Schwartz function, for example. But we will randomize them. We'll randomize those Fourier modes by multiplying for each k, multiplying by eta sub k, and this eta sub k is an IID normalized random variable. So this means that it has mean 0 and variance 1, okay? And we will call such data well prepared. The reason why it's called well prepared is because if I look at the variance of the initial data at k, so at the Fourier mode k, so this is the expected value of u hat of k squared, this is exactly given by n initial. And this n initial will serve as the initial data for my kinetic equation, okay? So this is the type of random initial data that is considered in this theory, okay? So by the way, if you're familiar with Boltzmann's theory, so in Boltzmann's theory, it is usually the random choice of initial data is stated in terms of an initial distribution of initial data, which is deterministic. One can state things exactly in that way in this setting. Here, I'm just being more precise about what this distribution is, okay? It is this corresponds exactly to a deterministic distribution of initial data, but I'm writing this distribution in terms of the how the initial data look like. Okay, and again, just as in the classical setting, the goal of the wave kinetic theory is to understand the distribution of those Fourier modes at later times in the limit when L goes to infinity and the alpha goes to 0. So this is a small alpha, and this is will replace the limit N goes to infinity and R goes to infinity in Boltzmann's particle theory. All right, so what does this kinetic theory tell us? So this is, I said, as kinetic conjecture. It says that in the limit as L goes to infinity and alpha goes to 0, this is called weak nonlinearity conjecture. This is part of the reason why this theory is also sometimes called weak turbulence theory. Then we have the following conjectures. First is propagation of chaos. So I'm starting with an initial distribution of the Fourier modes that are independent of each other. The point is that as I turn on the nonlinear interactions, they will stop being independent. There will form an dependence relation between them. But the key point and the very fascinating point from a mathematical point of view, in my opinion, is that once you take this limit, this independence is magically retained. Okay, you retain this independence after you take the kinetic limit. The second thing is the analog. We have an analog of Boltzmann's equation. So it tells us here the quantity of interest is the variance of the Fourier modes. So if I look at the effective dynamics of the variance of the Fourier modes, this is given by a kinetic equation that is called the wave kinetic equation. I will write it for you on the next slide. And so roughly speaking, what we have is that the expected value of the, or the variance of the Fourier mode is given by the solution of this equation at time t over t kinetic. So this is why I said here that this kinetic equation is rescaled to the kinetic time. So this kinetic time is 1 over alpha squared, and alpha is the size of the nonlinearity. I remind you of that. Okay, and so this is equal to that plus little of 1. In other words, this means that as L goes to infinity and alpha goes to 0, we expect this to be the limit of this to be given by the solution of the wave kinetic equation. Okay, and it is the solution of the wave kinetic equation with initial data and initial. Okay, that an initial appeared on the previous slide in my choice of the initial data for NLS. Okay, and finally, not only I can tell you what the variance of the Fourier modes is at later times, I can also follow the density or the law of these Fourier modes at later times. And this is something that can be derived. The limiting behavior can be dictated in terms of the variance and in terms of this wave kinetic equation that I will write for you over here. So the wave kinetic equation is right here. It's given by dTn is equal to k of n. So this is it's cubic instead of being quadratic in the Boltzmann case, and this is the collision kernel. It's given by this integral. So you're integrating over xc1 minus xc2 plus xc3 is equal to xc. And also you're integrating over xc1 squared minus xc2 squared plus xc3 squared minus xc squared equals to 0. So for those of you who are familiar, this is exactly the integrand that appears in Boltzmann's equation. So the measure that you're integrating against is for NLS, this is a property of NLS that it is really an exact analog of Boltzmann's equation. This is the same integrand. The same integral that appears in Boltzmann equation. The integrand is different. So this is the integrand. It is, you take n at xc1, xc2, xc3, and xc, you multiply them, and then you multiply them by this factor over here. So this is the wave analog of Boltzmann's equation. And this is a kinetic approximation that features the passage from the time reversible NLS equation into the time irreversible wave kinetic equation. This is time irreversible. It has an entropy that increases in the positive direction of time. And there's also an inhomogeneous version of this equation where instead of this dTn, you would have dTn plus xc dot grad x n. So this n in this case would be the function of t, x, and xc. Instead of just being a function of t and xc, that would be the inhomogeneous version. Today, I will restrict attention to the homogeneous setting, okay? Which is why there's no transport term on the left-hand side of this equation. Okay, so let me discuss briefly some history of this equation. So I'll start with the history in the physics literature. As we mentioned, the emergence of this theory was in the 1920s, and this kinetic formalism was formulated and generalized to many nonlinear wave systems. So for the context of water waves, this is called the corresponding equation is called Hasselman's equation. So this the same Hasselman that won the Nobel Prize this year or last year. In the context of anharmonic crystals, it's called the Fonum-Boltzmann equation, and there are many kinetic equation, wave kinetic equation in plasma theory as well. And it is indeed very much used in applications, particularly in oceanography, in terms of ocean forecasting, in crystal thermodynamics, plasma theory, etc. However, from the physical point of view, it seems that the most notable thing about this theory is that its strong implications about turbulence for nonlinear wave systems. I won't elaborate much on that, but I'll just say that formally what this wave kinetic equations gives conclusions very similar to those made in hydrodynamic turbulence. In particular, it gives us power law cascade spectra. So these come out as special stationary solutions of the wave kinetic equation that go by the name Kolmogorov-Zakharov spectra. And those were discovered by Zakharov in the 60s. And there are some first mathematical works trying to understand those spectra. Okay, but in a way, we are still very far from putting this part of the theory on rigorous foundations, even though, as we will see today, we have done considerable progress in terms of putting the wave kinetic equation on rigorous grounds. So in terms of history in the mathematical literature, so this wave turbulence theory has fundamental mathematical implications on the long-time behavior of solutions for dispersive and wave equations. So the initial focus of the wave turbulence theory was on constructing solutions that exhibit growth so the initial focus of the kinetic of this wave turbulence theory is in the mathematical literature was on constructing solutions that exhibit, as I said, growth of Sobolev norms. So this is the growth of the Sobolev norm. This is the HS norm. So you can see the key feature about this Sobolev norm is that it penalizes high frequencies much more than it penalizes low frequencies. Okay, so the wave turbulence theory predicts that the energy of the solution will move from low frequencies towards high frequencies, and in the process, this Sobolev norm should increase. This was the focus of the mathematical research related to wave turbulence, and it mainly started by Bourgain in the 90s. Okay. The most influential work here is that in this direction is that of Colliander, Keel, Safina, Takaoka, and Tao. So what they prove is that they prove that there exist solutions of the wave kinetic equation that exhibits arbitrarily large but finite growth of Sobolev norms. Okay, so what this means is that there are solutions that start small in HS and at later times become large in HS. However, those solutions that were constructed are in a way very special, and they are far from being generic solutions. So whether this behavior is generic or whether there exists solutions that exhibit infinite growth of Sobolev norms is an outstanding open problem for NLS on the torus, despite some partial results in those directions. Of course, again, the reason why we would like to understand this kinetic approximation is that it would give us a very strong insight on this open problem, whether there exists solutions that exhibit infinite growth of the Sobolev norm, or whether this behavior is generic or not. Okay. But again, in terms of mathematical reasoning, the central question actually is whether we can give a rigorous justification of this kinetic approximation, whether we can, if you like, the elephant in the room is to justify this approximation, whether indeed the variance of the Fourier modes of the solution at later time is well approximated by the solution of the wave kinetic equation, which is exact analog of Lanford's theorem in the case of the Boltzmann equation. Okay, and this is of interest both from mathematical and physical reasons. Okay, so even though I told you what the conjecture is, what the kinetic conjecture, I formulated what the kinetic conjecture, the analogy with Boltzmann's theory is still lacking one aspect, and the aspect is scaling laws. Remember when we talked about Lanford's theorem, Lanford's theorem tells you that the one particle density function is approximated by solutions of Boltzmann equation in a very particular scaling law. That was the Boltzmann grad scaling law. Okay, this one over here. Okay, so even also in this theory, we need to dictate the relative rates where the limits L goes to infinity and alpha goes to 0 are taken. Okay, so L goes to infinity, alpha goes to 0 will also cannot be taken. We'll see that they cannot be taken arbitrarily. They have to be taken in a particular way. Okay, so this is what we mean by scaling law, which is the relative rate of the limits L goes to infinity and alpha goes to 0. Okay, so a priori, you might start by saying, I want to start without restricting myself at all. And I want to consider all scaling laws, alpha equals L to the minus gamma. So if alpha is going to 0 and L go to infinity, then all the scaling laws can be written in this form, alpha equals L to the minus gamma, but I would allow gamma to be between 0 and infinity, including 0 and infinity. So when I say gamma equals to 0, I mean by that, I would take basically L to infinity first, and then take alpha to 0. Okay, and vice versa for gamma equals infinity. Okay, but it's not it doesn't take too long to understand that not all scaling laws are admissible. Just as similar to the case of the Boltzmann, where not all scaling laws are admissible. And the admissible scaling laws depend on the shape of the domain that you're working on. For example, here we are working on a box of size L. I can consider this box not to be a square box, but sort of a rectangular box or rectangular parallelepiped. And then in that setting, the range of scaling laws that are admissible, or the range of scaling laws that could give you a kinetic theory, depends very much on those aspect ratios of the box. So if you don't want to put any assumptions on the aspect ratios, the biggest range of scaling laws is basically 0 less than gamma less than 1, okay? Less than or equal to gamma less than 1, okay? So this is, you need to take L to infinity and alpha goes to 0 in such a way such that alpha equals L to the minus gamma and gamma is between 0 and 1, okay? This is the square box. So if you impose Diophantine conditions on the aspect ratios, then you can increase this range a little bit. But again, this is a rather technical point, so I'll not go into it today. Okay. All right. So let us get to the mathematical results on this question. So this question has a lot of flavors to many other similar and close by questions. The first work that is in this direction of, or this broad direction of research, is that of Erdős, Salmhofer, and Yao, or the first work that seems to be most or closely related is that of work of Erdős, Salmhofer, and Yao, and that work considered the linear Schrödinger equation with random potential. Okay, and so this is in around 2008. Then there was a very influential work of Lucan and Spohn, who studied the nonlinear problem, but they were studying something else for the nonlinear problem, basically time correlations of the invariant Gibbs measure in that setting. So it's not the same problem, but this is closely related. Now, there are some works in the stochastic setting on this problem. So basically, instead of taking random initial data, you would add a stochastic force to the equation. Here, there are works of Pfau, Daimov-Kuxin, and Daimov-Kuxin of Vlatuts, so who have studied stochastically forced equations. But in the first attempt at the full problem, so you keep the equation deterministic, and you only randomize the initial data, was done in joint work with Buckmaster, Germain, and Chata in 2019. And in that setting, we put ourselves in the setting of the irrational torus. So this is a torus with the aspect ratios are rationally independent and in dimension d greater than or equal to 3. And in that setting, we did justify the approximation that needed approximation, but there's a big caveat is that we only justified it for very, very short times. So short times that are considerably shorter than the kinetic time scale. Okay, so if I go back to this conjecture that I would like to prove is this approx conjecture, typically, strictly speaking, you want to show this conjecture for times that are multiples of the kinetic time scale, because then you're talking about n at times that are order of 1. So in the first work with Germain, Buckmaster, Germain, and Chata, we're only able to reach times that are very much smaller than the kinetic time. Okay. Where are we? Okay, here. Okay, so then in a couple of later works in 2019, one jointly with Yu Deng and another independent work of Collot and Germain, this approximation was improved to considerably longer intervals. So we were able to justify this approximation basically for times that are L to the minus epsilon times the kinetic time, where this epsilon can be taken to be arbitrarily small. Okay, we weren't able to do that for all scaling laws. We were able to do that for two particular scaling laws, gamma equals 1 and gamma equals epsilon. Okay, and the work of Collot and Germain also gave the result, the same result for gamma equals 1. Okay, and there has been further developments by Collot and Germain in later works. Okay, so but the problem with this is that even this previous work of ours and that of Collot and Germain does not quite reach the kinetic time. You're still considerably smaller than the kinetic time. So all those works fail to reach the kinetic time scale T kinetic, and a full justification of the equation should reach those kinetic times, should reach delta times the kinetic time, where delta is independent of L and alpha. Okay, that would be put the theory here on the same setting or the same level of in terms of the time as the Boltzmann or Lanford's theorem for Boltzmann equation. Okay, and this is the subject of the main theorem for us today. So this is a joint work with Yu Deng that a couple of joint works with Yu Deng that we published last year. So here we are able to give a full mathematical justification of wave turbulence theory that includes a rigorous derivation of the wave kinetic equation and the other things that were conjectured and mentioned before, as I would state now. Okay, so here's the setting. So we consider NLS on a periodic box in dimension d greater or equal to 3. We take an initial to be greater than or equal to 0, and this is the initial data for the wave kinetic equation. So here I say that an initial is a Schwartz function. This is an overkill. You just need it to be sufficiently decaying and sufficiently smooth. Finite orders of decay and finite orders of smoothness are sufficient, but we don't quantify it here. And we take the initial data for NLS to be well prepared as we described before. So it is given by the modulus is given by square root of an initial, and then we randomized by eta sub k, and those eta sub k are IID random variables. On a first reading, you can think of those eta sub k as being Gaussian, but the theorem is much more general than that. So we can take eta k so that the only requirement is that their low is rotationally symmetric and has exponential tails. Okay, and then in turn we get to the important point of scaling laws. So we assume that L goes to infinity and alpha goes to 0, such that alpha equals L to the minus gamma, and gamma is 1 or close to 1. Okay, so it's in this window. Okay, and in that setting, remember always T kinetic is 1 over alpha squared. We have a technical assumption when gamma is exactly equal to 1. In that case, we assume genericity assumption on the aspect ratios of the box. So the box has to be irrational in this special case when gamma is equal to 1. Then the theorem says the following, that there exists delta, which is fixed, and absolute constant nu, such that the following holds, exactly what we want. The variance of the solution is approximated by the solution of the wave kinetic equation, rescaled at the appropriate time, plus an error that goes to 0 as L goes to infinity. And the key point is that this approximation holds for times that are 0 up to delta times T kinetic, where delta is a fixed number, okay? So, so here, as before, N solves the wave kinetic equation with initial data and initial. Okay, so let me continue the main theorem. Now, suppose this came in a second work with Yu Deng. Suppose that you take K1 up to Kr to be R distinct wave numbers. Then we have propagation of chaos. The random variables, U hat of Tkj. So remember, U hat initial at Kj were taken to be independent from each other. As I said before, as you turn on the nonlinear interaction, they start interaction and they stop being independent. But the magical thing is that this independence is retained when you take the kinetic limit. So as you take L goes to infinity, the random variables you had of Tkj retain their independence again. So this is what is called propagation of chaos. And then we can also not only specify the variance of the Fourier modes, but we can describe precisely the law of those Fourier modes. So the law of U hat of Tk converges to the density function rho k of Tv. So this is a density function for the frequency or for the wave number k. So it depends on time and it depends on V, where V is now in R2, okay? Because it's the density of a complex number, okay? So this is the law of U hat of Tk, and U hat of Tk takes its values in complex numbers or R2. Okay, and the equation satisfied by the law of U hat of Tk is exactly that. Where here sigma k and gamma k are just functions of time that are constructed from the solution of the wave kinetic equation. They are explicit and constructed from the solution of the wave kinetic equation. And then here's another fascinating property that you also get. Also was conjectured by physicists, is something that's called propagation of Gaussianity, which tells you that if you take your initial data to be Gaussian, so if those eta k were Gaussian, then the law of the Fourier modes in the kinetic limit is Gaussian again, okay? So if you are Gaussian initially, as time goes by, as when you turn the nonlinear interaction, you stop being Gaussian, of course, because you're interacting with each other. The Fourier modes are interacting with each other. But somehow magically in the kinetic limit, this Gaussianity is retained and is reinstated. The only difference is that the variance of the different Fourier modes is given by the solution of the wave kinetic equation. Okay, so by the way, after we derived this equation, we realized that it was actually written in the physics literature in a couple of works that are mentioned over here. Okay, so this was all confirming again the conjectures of that were given by physicists. Okay, so some remarks on the results. So these results provide a full mathematical foundation of wave turbulence theory. By answering all three fundamental questions: propagation of chaos, derivation of the wave kinetic equation, and the evolution of the limiting density. So I should definitely remark on scaling laws. So so as I said, when the scaling law is gamma exactly equals to 1, this corresponds to the kinetic time scale being L squared, because remember, gamma is 1 means that alpha, the scaling law tells you that alpha is equal to L to the minus gamma. So the kinetic time scale is 1 over alpha squared. So it's always given by L to the 2 gamma. So when gamma is 1, the kinetic time is L squared. And here, as I mentioned, we need to impose some genericity conditions on the aspect ratio of the torus. These are just technical assumptions. They come from one part of the proof where you need a little bit of number theory. But I want to emphasize that those conditions are not needed whenever whenever gamma is less than 1, okay? Even in the parts of the proof that I haven't announced in the theorem here, because we are in the process of treating all scaling laws gamma between 0 and 1, you do not need any genericity conditions whenever you're dealing with scaling laws gamma between 0 and 1. Okay, so why did we start with the scaling law alpha equals L inverse? Because it carries a particular importance, and it carries particular importance because in this setting, the kinetic time scale is L squared. Okay, and what this means is that you're talking about solutions on the torus of size L at time L squared, which means that you can rescale this to the unit torus. So if you define V to be this quantity, then V solves the cubic NLS equation on the unit torus. Okay, and so this would allow us, this scaling law would allow us to transfer, for example, energy cascade dynamics from the wave kinetic equation to the NLS on the unit torus. There's another reason for that in terms of another big open problem, which is the invariance of the 3D Gibbs measure for NLS. I think I'm running out of time, so let me skip that. But the key difficulty in this problem is, or in both problems that I mentioned just now, is something that's called probabilistic criticality that hopefully we'll discuss in a minute. Okay, and in a way, this result is the very first probabilistically critical result, even in the parabolic setting. Okay, before I go to discuss the proof, I should mention the work of Safinan and Tran that also came up in last year. So there they considered a high-dimensional discrete KdV equation, d greater than or equal to 14, and the problem of deriving the associated wave kinetic equation. So their main result falls under the stochastic setting that I mentioned a few slides ago. So they consider the equation in the presence of a stochastic or noise term in it, so this is a Stratonowicz stochastic noise term, which effectively keeps randomizing the phases of the Fourier modes at all times. And in this setting, they give a derivation of the wave kinetic equation at the kinetic time scale. It should be pointed here that the noise is crucial for that result, because it provides additional randomizing mechanism to the equation, which is absent when you keep the equation deterministic and only randomize the initial data. They do have a conditional result in the absence of the noise when they only randomize the initial data. But as I said, it is conditional. So they have to assume certain a priori estimates on the solution to hold in order to get that result. They verify that those a priori estimates hold for some very restricted set of initial densities. Okay, so that's all I want to say here. All right, so in the remaining, 5 to 10 minutes, or how much time do I have?
I think you can go to like 55, please.
Okay. So the remaining 8 minutes, let me give you a very quick idea of the proof. So the main idea of the proof, which is common in all those diagrammatic proof, is to expand your solutions in terms of power series. So you write U as U0 plus U1 plus UN plus a remainder, where those are essentially the iterates of the solution. This is the 0th iterate, this is the first iterate, this is the nth Picard iterate. Okay, and each of those iterates will be a multilinear Gaussian expression because, well, I should remove here Gaussian. It's not necessarily Gaussian unless the initial data is the Gaussian, but it's a multilinear expression that involves the random variables eta k. And each of those U sub I can be represented in terms of what's called Feynman diagrams. So what are those? So this U0, the initial or the 0th iterate is represented using a simple vertex. The U1 is represented by a ternary tree with one branching node. So this would be the root, and then it has 3 children, and those 3 children, we decorate them using wave numbers such that k is equal to k1 minus k2 plus k3. And in general, if you look at U2, then you would have a tree that has 2 branching nodes. So these are the leaves of the tree where you would have wave numbers. And if you are talking more generally, if you look at the nth branching nth iterate, then you would get a tree that has n branching nodes. We call that the scale of the tree. Okay, so this is, for example, something like this. Okay, so if I look, so this means that U hat can be represented as sum of decorated trees. These are what we call the diagrams, and such that the nth iterate is the sum of decorated trees of scale n. Okay, ternary trees of scale n. Okay, ternary means that each branching node has 3 children. Okay, over here. Okay, so now I'm interested in looking at the variance of the solution. This means that this is, remember, this is just a copy of U multiplied by a copy of U bar. And so I expand U in terms of trees, expand U bar in terms of trees, and then multiply that. So I get basically products of trees, something like this. Okay, so in the expansion of the variance, I would get a paired couples of trees. So that the variance can be written as a sum over paired couples of trees like this. But the key point is that the leaves of those trees are paired to each other. Okay, and they are paired to each other because we are taking this expectation. By taking this expectation, this essentially pairs the leaves of those trees. So I denote this by using colors. So here, this leaf is paired to this leaf because they're both red. This leaf is paired to this leaf, etc. Okay. So the thing that you want to keep in mind is that this variance over here can be written as a sum over paired trees. Okay. Now there are 2 enemies that one has to overcome. The first enemy is that there are a factorial number of such couples. Okay, there are factorial number of such diagrams, and this is a major obstruction to proving the convergence of this power series. Okay, when you have a power series and a factorial number of terms there, then this is quite tricky. And the second problem is this criticality that I have basically mentioned before, which is the probabilistic criticality. And roughly speaking, this probabilistic criticality tells you that the n plus first iterate is only better than the nth iterate by a factor of delta. Okay, so maybe let me skip this criticality because I'm running out of time, but I will discuss the second and in a way more serious enemy, which is this factorial divergence. So the factorial divergence tells you that, remember that the number, so this, if I look at the nth iterate and the variance of the nth iterate, then this is a sum over n factorial couples. Sorry, I dropped my pen. N factorial couples. And if all those couples have, they have the same size, or if I can only bound those couples by the same number, which is delta to the n. This is in the previous slide, but I skipped that. If I only can bound those all those couples by the same bound, then we are doomed to failure, because then you have delta to the n times n factorial, and this is a problem. Okay, so the strategy, or the key strategy, is the following. So the key strategy of the proof is to classify couples into groups, okay, such that those groups that saturate or almost saturate the worst scenario estimate, which is this thing, delta to the n, there are few. There are not so many of them. They're not factorial, many of them. There are few in the sense that they are exponential rather than factorial, okay? Whereas all the remaining couples, okay, they satisfy much better estimates than the worst case scenario. And in particular, they have to feature a gain as a power of L that is sufficient to offset this factorial divergence, to offset the fact that there are factorially many of them. So in other words, this requires us to do two things. The first thing is to identify those couples that have the biggest couples that have saturated or almost saturated bounds. And we need to show that there are only factorially many of them. And the second step is a sort of a rigidity theorem that tells you that once you adequately remove the couples, those couples that saturate the bounds from your pool, you are left with couples that feature a large gain that is large enough to offset the factorial number of couples. So in terms of the first step, which is identifying the couples with saturated bounds, there's good news and bad news. The bad news is that there are more couples than you expect that saturate the bounds. So strictly speaking, when we came into the problem, we were expecting that the couples that saturate the estimates are exactly the couples that converge order to order to the iterates of the wave kinetic equation. And these are what we call the regular couples over here. Okay, these are the couples that you want them to be the biggest ones, because these are exactly the ones that give you the wave kinetic equation. But life is not too simple. So it turns out that there are two other families of couples that saturate those bounds. And one family is called what we call irregular chains. We, strictly speaking, we were expecting those because from our previous work, we identified those as an obstruction in our previous work. But the nice thing about them is that they exhibit an elaborate cancellation. Okay, those irregular chains. So there's an elaborate cancellation of couples that allows us to basically absorb those irregular chains. Then there's a third family that I don't have time to discuss, but also has a redeeming feature that also allows us to absorb it. But the key point is that the good news is that even though there are three families, all those three families, there are C to the n of them. There are only exponentially many of such large couples, not factorially many large couples. So this brings me to discussing the rest of the couples. So the fact that all the remaining couples, which are factorially many, remember, feature again is the content of our rigidity theorem, which in a way it is, if I had to pick a theorem, this is the most important theorem in the paper. So the theorem says that if one performs a type of surgery on an arbitrary couple and you remove all the structures that saturate the bounds, so you remove from this couple all the regular subcouples or the irregular chains, all the type 2 molecular chains that were on the previous slide, so all the structures that lead to almost saturated estimates, you do a surgery and you remove them from the couple, then you're left with a reduced couple of size R. And the key point is that the estimate on this couple features a gain that is of the form L to the minus CR. In other words, the gain depends on the size, is comparable to the size of this couple. And this is crucial. The reason why this is crucial is that this is the kind of gain that allows you to offset the factorial divergence. The reason for that is that there are R factorial many of those couples. So once you do the surgery, the number of those couples is R factorial. And the gain is L to the minus CR, but L to the minus CR times R factorial is an error, provided your R is less than a logarithm in L, okay? And this is something that we can choose. We can allow R to be at most a logarithm. Okay, so this proof again is the most sophisticated proof in the paper, and it involves recasting the problem of counting couples into counting combinatorial families that we introduce and call molecules, like here. So this couple is transformed into such molecule, and then we do the analysis on this molecule rather than on the couple. I don't have time to elaborate too much on that, but the last thing I want to say is that the analysis of all those couple families that I mentioned in the last few slides, regular couples, irregular chains, type 2 chains, each one of those requires a different type of argument. And this ranges from combinatorial constructions, like the ones that we do here, to analytic ones, and also number theoretic ones. You need some number theory in order to estimate precisely the regular couples and their contributions. And once this picture is made clear, I only told you how to estimate the iterates basically in the Feynman diagram expansion. Over here, I only told you how those things are estimated. Then there's the remainder, which is also another story, but basically the good news is that this story, once you understand how to bound the iterates, you have a very good set of tools in order to bound the remainder. Okay, and I will stop here. Thanks for your attention.
Okay, thank you very much for this very nice talk, very impressive result. So any questions from the audience?
Zaher, so what happens when the random variables are more heavy tailed, not exponentially decaying?
Oh yeah, that's a good question. I don't quite know, to be honest, what would happen. So basically what so in our first paper, we dealt with the case when the random variables were exactly Gaussian, and there we relied on Gaussian hypercontractivity estimates. In the second, we generalized this to random variables that have exponential tails. And basically the reason for that is because we are doing an expansion that is an infinite expansion in a way. This expansion diverges with the number of terms in the expansion. And in that case, we need bounds on when we look at, for example, expected value of eta k to the 2r. Okay, we need that this is bounded by CR factorial. Okay, in order to do our estimates, because this is related to the factorials that I mentioned, and they appear later. So we are able to absorb factorials like this one. We're not able to absorb things that are much bigger than that. So if you don't have such an estimate, which is equivalent to having exponential tails, then there's trouble. I don't know. I don't even know if the theory would hold.
Yes.
I don't know. Yeah.
Thank you.
So any other questions? So Zaher, what happens if the nonlinearity is in a different form, like even a power nonlinearity with a different exponent?
Yeah, that should be perfectly fine. If you have a cubic instead of, as long as the nonlinearity is a analytic nonlinearity, something like u squared u or u to the 4u or something like that, then the same proof or the same should go through. It needs modifications, but the theory is expected to hold there, and I would expect a very analogous theorem to hold as well.
Okay. Are there any other questions? Okay, so let's thank Zaher again for this very nice talk.
Thank you.